In fatty acid breakdown or beta oxidation, you break down a fatty acid from the bottom up, releasing acetyl-CoA. How it works is basically CoA, so coenzyme A, comes in and acts as kind of scissors that get stuck on what they cut. So they're going to kick off the acetyl-CoA, leaving you with a shorter fatty acyl-CoA. Another CoA comes in, it gets stuck on, it cuts a piece off. Another comes in, cuts a piece off. Another comes in, cuts a piece off. Until, well, you've reached the end. And this was the first acetyl-CoA that you added when you were actually synthesizing fatty acids. So kind of like an airplane, the people on the back of the plane load first, they get in first, and then they come out last. Similar with our fatty acid synthesis. The synthesis itself is a little more complex. We start with acetyl-CoA, we carboxylate it using acetyl-CoA carboxylase. This is we spend energy in order to add a CO2, but then when we get malonyl-CoA. Malonyl-CoA is a key regulatory molecule because it's only basically going to be present if you're making lipids. And so it's actually going to inhibit the fatty acid breakdown by inhibiting CAT1, or basically the enzyme, the transporter that's going to help make it so that those fatty acids can get into the mitochondria, which is where the fatty acid breakdown occurs. In this case, we get this malonyl-CoA, and that CO2 that we added, now we're going to actually release it. We're going to transfer this malonyl-CoA to this acyl carrier protein, which is part of this fatty acid synthase. On this acyl carrier protein, you have a part that's basically exactly like CoA, except that the one end of it's different. But the important end, the end with the sulfur that actually makes the linkage, is going to be free. And so this is going to get transferred onto this acyl carrier protein. Now the acyl carrier protein with this malonyl acyl carrier protein, basically this is going to come and it's going to attack this chain, our growing chain, giving us a longer growing chain and kicking off the CO2. Now what's going to happen is that we're going to get some steps where we're going to basically be reducing this, and ultimately what we're going to do is then we're going to transfer this chain from the acyl carrier protein onto a sulfur residue in a cysteine at another site on this big protein. Now we can get this whole thing happen again. We'll get another malonyl-CoA come in, get attached to the malonyl acyl carrier protein, which is just a part of our fatty acid synthase, and then that'll kick off the CO2, it'll add, we'll get our chain elongated 2 carbons further and keep going and keep going. Because we're adding 2 carbons at a time and we're removing 2 carbons at a time, this makes it so that we typically have these these even numbered fatty acids that are perfect for breaking down into acetyl-CoAs. If we end up with something where we have an odd chain fatty acid, where we would end up with a 3 carbon product at the end, propionyl-CoA. In that case, what we do is we actually carboxylate it to give us a 4 carbon product. We rearrange things a bit and we get succinyl-CoA, which could enter the tricarboxylic acid cycle that way.